Hi friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 1339. Maximum product of splitted binary tree. In this video, we're going to share some solution formats based on traversal. First, I'm going to read through the problem statement to digest the requirement or task. And then we do the analysis, and finally we share the code. First, let's look at the problem statement. Given the root of a binary tree, split the binary tree into two subtrees by removing one edge such that the product of the sums of the subtrees is maximized. So we need to return the maximum product of the sums of the two subtrees. Since the answer may be too large, so we need to return it modulo this constant. So notice that we need to maximize the answer before taking the mode and not after taking it. So that's just a notice or a remark. So let's have a look at the two examples here. So in example 1, so the output is 10. So it's corresponding to remove the red edge to split the tree into two parts. So in this case, so one tree has a sum that is 2 plus 4 plus 5, that is 11, and the remaining is 10, right? So we have 11 times 10, that is 110. So this is the first example. So you can also try to remove the other edges to split into two parts and compute the product and compare with this 110. So this now let's look at example 2. So in example 2, so the output is 90. So it corresponds to remove the red edge. So in this case, the two subtrees have one is 6 and the other is 15. So 6 times 15, that is 90, right? So here actually for this problem there is a invariant, that is the total sum of the two subtree sums. So this sum is always equal to the total tree sum, right? So before we do the analysis, let's look at the constraints. First, the number of nodes in the tree is in the range given by the closed interval, with 1 and 2 and the other 5 times 10 to the power 4. So we should pay attention to this latter number. It actually gives us a upper bound for the problem size. The second constraint is that the node values are in between 1 and 10 to the power 4. In particular, it's all positive. They are all positive, right? So with that said, we are ready to do the analysis. First, the method we are going to use or the solutions are based on traversal. So here, the main observation for this problem are the following. So assume the total sum of the full tree is S, and then cutting an edge with splits will split the sum S into two parts. So here it's not with, will. We'll split the sum S into two parts. So one is a full subtree sum, and the other, let's call this S subtree, and the other will just be S minus this S subtree sum, right? So for example, in this example 1, so the total sum is 21. If we remove the red edge, right, so one subtree is this one, so 2, 4, 5 corresponding to 11, so the other will be 10, right? So if we delete the edge corresponding to this 1, 3, right? So we will have a subtree sum that is 3 plus 6, this is 9. And then the other part will be 21 minus this 9, that is 12. So the product is 108 in this case. So in this example, as we explained, the return shall be 110 if we check all possible subtree sums. So this observation actually gives us hint on how to do the coding. So the third part is about the coding implementation. So we could actually find all the subtree sums, so which is actually very easy task. Then we just find the maximum of S minus the subtree sum times the subtree sum for all the subtrees, right? So here, actually, there's a comment I want to mention. So, because if we would like to make some optimization or early stopping, so it's doable. So we do not plan to complicate things here. So the idea is that, so the function on A, let's call it fa, which is S minus A times A, is symmetric with respect to the line S minus A equals A. In other words, A equals S over 2. So this function is increasing in the interval from 0 to A over 2 and is maximized at A equals S over 2 if we do not consider the number types. So therefore, we could check subtree sums for all these A such that A is less than or equal to S integer division by 2 plus 1, right? So that's just some set comments. So with that said, we are ready to do the coding. So for do the coding, I'm going to share two versions. So the first version is just a translation of the above analysis in a verbose way, right? So let's call it V1, so more verbose. So this is helpful for us to understand the overall logic. So here I'm going to introduce a variable. So let's call it introduce a attribute. I'm going to use this attribute for easy update. So you can use non-local variables if you like. So first, I'm going to write a hyperfunction called getSum. So we're going to get the subtree sums, right? So I'm going to count this, put a root, a node here, and then first, if not root. So we're going to return 0, right? So this null tree corresponding to a sum that is 0. Otherwise, so we just need to return getSum root left plus root value plus getSum root right. So this is actually a very easy recursion format. So then we can get the total sum. So that is getSum root. Then I'm going to do a traversal. So for this, we can do all kinds of traversals. So here, let me. I'm going to do this. So I'm going to use pre-order traversal. See, let's use stack equals root, and then we're going to do the standard while loop for pre-order traversal. So if you are not familiar with pre-order traversal or any other traversal for binary tree, you can check our videos in the channel. So with that said, let's first do this stack pop. So now we have this node, right? And then let's first get the temp. This is the getSum of the node, right? And then we're going to update the result to be the max of its previous state, and then the current product, that is S minus this temp, and temp, right? And then if we do not include this, so this will be the standard pre-order traversal. This is a problem logic, right? So we just need to add a tiny bit of line to incorporate the problem logic in the standard pre-order traversal. So if node right, notice that I'm going to first check the node right, the right subtree, to make it a standard pre-order traversal. But though in this problem you can do whatever order you like. So stack append node right, and then I'm going to copy this one and check node left, right? So let's call it left. So left. So once we finish this, so we're going to return the result in the sense of modulo a constant, that is 10 times 10 to the power 9 plus 7. So this forms a solution format for this problem. Let me do a check. Yeah, it passes the first example. Now let's look at the generic case. it's running slow, so let me add a cache here. Let's run this again. Yeah, it passes all the test cases. So this is one version of solution, but actually we have lots of repetitions here when we do the iteration here. So now let me write another solution format to optimize a little bit. So though essentially the same solution. So here I'm going to call this one version v1, and then what we are going to do is that, so first I'm going to store all the subtree sums. Let me do this subtree sum. So I'm going to use a set, right? And then I'm going to write a depth first search function or something like that, a traversal. So let's call this f. Just you can think of f as a helper, right? So if not root, so we're going to return 0, right? And then I'm going to call it for left subtree sum and the right subtree sum, right? And then we're going to self subtree sums. I'm going to add, right? Because L plus R, let's see, root value plus R, right? Then also we need to return this L plus root value plus R, right? So this is the hyperfunction. Actually, it's the depth first search, if you like. So now let's first call this function sfroot. So this s will be the full tree sum, right? And then what we're going to do is to return this guy, max s minus the subtree sum. Let's call it item. For item, let's see, we need to multiply this guy by item, right? For item in self subtree sums. So here, after we compute the maximum, we need to modulo this number by this one, plus 7, right? So let's test this case, right? So we can run item. So let me item. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So actually you can, if you like, you can use cache here. Let's test it again. Yeah, it passes all the cases anyway. So with that said, I guess that's about it for a solution to this problem. So in this video, we shared solutions. We shared two formats based on traversal. The first one actually is very verbose, so there are some repetitions, but we here actually used a recursion to compute the subtree sums. Actually here, if we call this, we can get all the tree sums, but we get the subtree sums using the while loop, which introduces repetition. So sometimes if you do not use cache, it still can pass, but you use cache, in general it passes all the test cases. So in the second version, so let me make this one v2. So we did some slightly optimization. So here we actually introduce this subtree sums set, and then after we do the traversal, so we get all the subtree sums, and then we compute the maximum product, and then according to the problem requirement, modulo a big constant. So with that said, I guess that's about it for this video. So we have a playlist on tree related problems, and also we explained all kinds of traversals on the trees and the graphs. So you are welcome to check out those videos in our channel. So thank you.